Hello everyone, my name is Jonas Vernica and I'm a research assistant at Aalborg University, and in this video I'm going to give a short presentation regarding the advanced reliability tool for the design of power electronics that we have developed here at the Center of Reliable Power Electronics. First, I'll briefly introduce the study case application that we are going to be looking into, followed by a walkthrough of the reliability tool. I will end this video presentation with some conclusions and some of the upcoming features that will be included in the future release of the tool. A typical PV application is chosen as the study case, where a two-level three-phase converter connects the BP365 PV panel to the grid. Moreover, an LCL filter is connected to the grid side and thus completing the system application. The inputs to the system are the field measured data of the solar irradiance and ambient temperature. These emission profiles have been recorded during the course of 1 year with a sampling time of 1 minute. Finally, the power module that we will be investigating with the help of the reliability tool is a 50 amp 1200 volts Infineon module. Next, we can move on to the presentation of the tool. The general flow of the tool can be seen in this figure. The environmental emission profiles will represent the inputs to the PV system model. Here the user is required to include the emission profiles and the system level specifications such as DC voltage, switching frequency, and grid parameters. The dynamic behavior of the system under the given emission profiles will be used in the power loss model in order to compute the total losses generated by the power devices. Next, the device power losses can be translated into the junction, case, and heatsink temperatures according to the employed thermal model. Finally, the thermal loading of the device can be used in order to determine accurate and valuable reliability information such as total accumulated damage or an estimated number of years of lifetime. The tool, together with the graphical user interface, have been built based on MATLAB and have been packaged as a MATLAB app. This will allow the user to simply initialize the tool from the MATLAB application toolbar. Once the tool has opened, the user can choose from various applications such as PV, motor drive, and wind power generation. As mentioned before, in this demo version we will showcase the PV application. Next, the user can load the environmental emission profiles. By pressing the solar irradiance profile button, we can simply load the emission profile from an Excel file. Next, we will do the same with the ambient temperature emission profile. After loading the emission profiles, they will appear in the top plots of the GUI, and the user can move on to select the dynamics of the system. In this case, we will choose Synchronize, which will automatically load the simulation sampling time. Now that the environmental conditions under which the system will operate have been loaded, we can design the system level application. The user can simply change the inputs to the system from the sliders and by pressing the Update Variables button. Moving on to the power converter panel, the user can select the topology of the converter, the modulation technique, or the power module. Here the user has the option to select from some predefined modules or use the user input option where he can upload his own power module under given guidelines, which will be provided with the full version of the tool. The grid parameters can also be adjusted according to the application requirements. While the parameters for the LCL filter can be introduced manually by the user or tuned automatically based on some current ripple and current attenuation requirements. Finally, in the full version of the tool, the Special Features panel will be made available where the panel degradation and PV array size can be taken into account when assessing the reliability of the power devices. Once the system level application design has been completed, we can move on to the component level design. By pressing the Update Power Device button, all the parameters necessary for modeling the power losses and the thermal loading of the Infineon module can be computed. The parameters for assessing the power losses of the transistor have been extracted from the switching energy and conduction voltage curves. Similarly, for the diode, the parameters have been extracted from the reverse recovery energy and forward voltage curves. It is worth noting that all the mentioned curves are usually provided by the manufacturer in the datasheet, thus making the power loss model quite generic and easily applicable to most power modules. The same procedure is applied for the thermal characterization of the device. The thermal impedance curve provided by the manufacturer in the datasheet is used in order to extract the parameters needed for the multi-level Foster network. After selecting the cooling method, which will be natural cooling in our case, the user can move on to the simulation panel. By pressing the Run Simulation button, all the user inputs will be updated and the simulation of the system can begin. For this given application, the simulation runtime is approximately 1 minute, but I will fast forward to the simulation end time. Once the simulation has been completed, the user can see the resulting thermal loading of the power devices under the given environmental emission profiles and system specifications in the upper plots of the GUI. Additionally, the user can calculate the efficiency of the converter system or plot detailed graphs of the resulting system level waveforms, power device losses, and thermal loading. In order to correctly link the thermal profile data to a lifetime model, a rainflow counting algorithm needs to be applied. According to some user-defined junction and case temperature threshold, the rainflow algorithm will determine each cycle's amplitude, mean value, and on-time period. A more detailed view of the junction and case thermal cycles can be seen by pressing the Plot Thermal Cycles button. The outputs of the rainflow counting algorithm can then be introduced into one of the predefined lifetime models. In the full version of the tool, the user will also have the option to include his own lifetime models and adjust the parameters according to his data and past experience without being required to disclose or share his models. After selecting the desired probability of failure, known as BX lifetime, the reliability assessment simulation can be run. Once completed, the total accumulated damage of the device and the estimated number of years of lifetime will be made available to the user. Finally, all the data determined using the reliability tools such as device damage, thermal loading, and power losses can be exported as an Excel file, while the graphs will be exported as .png files. In order to summarize, a MATLAB-based reliability tool which takes into account the environmental emission profiles has been developed. The compact and user-friendly GUI allows for easy system-level and component-level modeling, while the state-of-the-art power loss and thermal models allow for precise assessment of power device losses and thermal loading. Finally, the tool allows for accurate lifetime estimation and easy access to reliability metrics. Currently, we're working on developing version 4.0 of the tool, which will provide the user more freedom when designing the system and component levels of the system. Furthermore, the reliability assessment of the DispLink capacitor and reliability assessment of multiple power devices at once will be made available, which will allow us to also include some system-level reliability assessment. If you are interested in future collaboration projects or just want to learn more about the tool, do not hesitate to contact us. Thank you for watching.